Okay, let's continue where we left off, and then briefly review the source shear strengths, and then I'm gonna show you a bite-sized video for the shear strengths, and then this 16 minutes videos gives you concrete understanding. Then I will finalize and then deal with the another two different triaxial tests conditions. Okay, let's consider these in situ conditions, which is the field conditions. And then as it is, at the moment, we don't have any structures. So these soil elements was subjected to vertical and horizontal stress only. Vertical stress, sometimes we call effective vertical stress and total vertical stress. And lateral stress is kind of a certain portion of vertical effective stress. And after construction, something kind of shallow foundation and buildings, additional vertical stress is imposed to the certain soil elements. So you can see the delta sigma, which is the additional vertical stress due to these shallow foundations. This condition are totally different. And then after constructions, we need to figure out soil's condition of these soil elements under certain loading conditions. It means that these stress conditions exactly simulated in our laboratory. What has happened in the soil under such loading conditions. This is the way we simulate the stress conditions in the lab. Mostly, this is soil sample in the lab, zero confining pressures at the moment. Then we simulate initial geostatic pressures, vertical stress and horizontal stress. Then after that, we apply additional vertical stress, and then we a bit rotate our axis, and then also additional shear stress. Because this additional vertical stress causes our soil's shear failure with a certain angle about our horizontal plane. These direct shear tests are similar conditions. This tau shear stress forced to get soil filled with this plane. It is also shear failures. In our school, we have these two equipments, and then this direct shear test is quite simple. We fix the bottom cups, and then we apply force only for the cup above. Then we can get soil's shear strength. But in this case, our failure plane is fixed. But triaxial tests, we don't know the exact failure plane after the tests. This is the triaxial tests configurations. Just take a look. This is our soil sample. How many openings do we have around the soils? Opening means valve. First one is poor pressure valve, right? We close this valve and apply load. Water in the soil tries to be drained through this line, but our valve closed. It means that once we put pressure sensors in this line, we can measure pore water pressures. So on drain tests, we always can measure pore water pressure. If let's say you open this tube while testing, water drain out through this, but zero pore water pressure because us opening the valve. But you can obtain water drain out, right? It means that you can check volume change of the soils. Hi, Prof. I just measured water from soil. But how come it is the identical to volume change? Yes. Soil squeezes out and pore space decreases. It means that water comes out. The amount of water from the soils exactly same as reduced void ratio. It means that we can infer soil's volume change, mostly decrease. Only one case is increase. Contracts, and already packed, dense enough. And then we apply additional load. The soil particle slide over. So the source volume increase due to dilation process. We have another channel, back pressure channels. It connected to on top of the soil sample. We apply back pressure. Why? Last week, I explained to you. And then this back pressure is related to saturation stages. I just uploaded, last week uploaded reading material. You can take a look and find out what is the saturation stages. And then the back pressure, how can the back pressure implemented in the saturation stages? And we have another channel, cell pressures. This is not linked to soil, but these cell pressures are connected to in the cell. It means that this cell pressure, sometimes which is the water pressure or air pressures. In our school, which is the air pressures. This air pressure apply the soil sample confining pressures to simulate soil's in situ stress. It looks quite simple, but underneath our cell, this panel, we have a lot of channels, a lot of sensors, and then very thorough control systems to maintain applied load. Okay? So I hope that you're supposed to conduct these triaxial tests. First step to prepare your soil sample and then mount your sample on the machine, and then you can control system to apply desired stress, confining stress, and then desired deviator stress. Then we we wait for a while, about 20 to 30 minutes to achieve 20% strain. Your stress and strain increase, and then if the strain is exceed the 20%, you can stop. So we have different types of triaxial test. This is the confining pressure steps. In this step, we can choose whether we open the drain valve or not. And also we have consolidation step. Oh, sorry, the loading step, applying the deviator stress. In this case, we also decide the opening the valve. After this, we will get the soil fail with certain failure plane. Consolidated drain tests, C, D tests, C, U test, U tests. So last week I explained to you the CD tests procedures. Basically, we have two steps. One is the consolidation. Second one is the deviator stress. And then if this stress keep on increasing, and then if the pressure reach to the failure stresses, you will get your soil sample failed. CD means consolidated drain. It means our valve connected to port pressure channels always open. It means that probably we can't measure port pressure, but we can measure volume change. Understood? So open, zero port pressures, and then the applied confining pressures became effective stress. Because effective stress is total stress minus port pressures. Currently port pressure all are zero. And then we apply deviator stress delta sigma, and still our drainage valve open, zero port pressures. And then this increment of the stress, which is the deviator stress, became effective stress. At failure conditions, this one just turned to delta sigma F, stands for failure. Sigma prime 1, F, failures. The denotes and terminologies, in terms of symbol, is sometimes very different with the different university, different researchers. But the physical meaning all are same. So in your exam, you can't exactly remember this symbol, it's okay. Just create your own symbol. Then clearly mention that, for example, this derivative stress finally became effective stress in the CD tests. Then I can understand what you are trying to say. I don't care about delta sigma equals to delta sigma prime 1. I don't care about this symbol, the naming, but I will look at your intentions, what you try to explain. So that's why do not leave as a blank. Do not write non-relevant contents. Just keep thinking, try to write something to answer the questions. Then there should be some chance what I can do for you. This is the saturation stages, and then last week I've explained, and then hopefully you are familiar with this figure, because all these figures get from that reading materials. Let's say I asked you, how do we get our soil sample saturated in triaxial tests? How can you explain? You probably you write something, you draw such figures. Yeah, that's all. So after these triaxial tests of the consolidated drain tests, we will get such stress-strain relationships, and we supposed to have multiple tests with different combining pressures. And then we connect all, draw the straight line that touch all sort of our Mohr circles, which is the Mohr-Coulomb failure criteria failure envelopes. The angle is the internal friction angles, and the y-axis, the number is the cohesions. So from the CD test, we will get effective cohesion, effective internal friction angles. So we normally use these soil properties in the embankments for the long-term analysis, and even the Cooper Dam and some the CPG problems. This is a slope stability problems. So last week I stopped here, but while preparing this lecture, I found very useful video clips. So I will we all together watch this video, which is the almost 16 minutes, but it is worth to watch. Okay.
Whether you are a civil engineer constructing a skyscraper or simply an admirer of these towering structures, you might wonder, can the soil beneath really handle all that enormous weight? Won't the soil bulge or crack under such pressure? Well, the soil's ability to resist this cracking and shearing is called shear strength. We explored shear strength and how it's described by Mohr-Coulomb theory in our previous video. We want to know the shear strength of the soil, and how much load it can withstand before it shears or cracks, making the structure above unsafe. To determine the shear strength of the soil, scientists have developed different methods. Today, we will dive into one of these methods, the triaxial shear test.
Shear meaning the compressive loads, sometimes vertical loads. Sometimes we call this load as a shear because after this load, our soils failed in a shear manner. So don't be confused.
In short, we take a soil sample and place it inside a triaxial apparatus. This machine applies a pressure on the sample from all the sides and an additional axial stress until it fails. The stress at which it fails tells us its shear strength. The apparatus uses fluid, usually water, to apply the confining pressure.
In this case, our machine is air pressures.
Simulating real world conditions. To understand the whole process in more detail, let's dive into the triaxial shear test method. The triaxial shear test is a crucial method used to determine the shear strength and stress strain behavior of the soil samples. It can be performed on various types of soils, such as clay and sand, and the results help engineers understand how the soil will behave under different loading conditions. The test is performed on a cylindrical sample of soil. Usually, the sample's dimensions are kept at a length to diameter ratio of 2. For example, if the soil sample has a diameter of 50 mm, its length would be 100 mm. To set up the test, we place the sample between two porous discs and position this assembly on a pedestal of the triaxial cell. We then attach a loading cap over the porous disc and encase the entire sample in the rubber membrane.
This rubber membrane are prepared first with soil sample, and then we mount on the traction cell, and then we put also porous stone, and then finally we apply this loading cap.
Next, we fill the cell with water at the required pressure. This applies an all-around pressure to the soil sample, which we call cell pressure or confining pressure,
Correct.
denoted as sigma C.
Sigma C or sigma 3 or same symbols, but sometimes differently used.
We use a device attached to the cell to measure this pressure. The membrane protects the soil sample from being penetrated by the pressurized cell water. This confining pressure compresses the sample, causing the pore water pressure to rise. Water tries to leave the sample and the consolidation of the sample begins. However, consolidation can only happen if we allow the water to drain out. For this purpose, we provide a drainage valve to the cell. When this valve is closed, the water generates pore water pressure, which we can measure on a dial gauge. In this condition, the sample won't consolidate because water can't leave the sample, resulting in no volume change. But if we keep the valve open, the water flows out and doesn't generate pressure. Soil begins to consolidate. In this case, we can't measure the pore water pressure. Instead, we attach a volume change measurement system to the cell. The amount of water expelled from the sample is measured in a burette attached to the system. For a saturated soil sample, this measured volume of water is equal to the change in the volume of the soil sample.
This assumption quite available in our soil mechanics.
Once the consolidation process is complete, we keep the cell pressure constant and we gradually apply additional axial stress through a loading system called RAM. We slowly increase this axial stress until the sample fails. This additional axial stress is called deviator stress and is denoted as sigma D. Stresses and strains generated are noted and the test is repeated for another sample. But this time, the confining pressure is increased.
We completed one sample and then try one more time with the same sample with different confining pressures.
The same procedure follows and corresponding deviator stress is measured. The first phase of this test, where the sample is subjected to confining pressure from all around, simulates the soil element's environment in the natural soil deposits. The second phase, where we apply an axial top load to the sample, simulates the condition where such a soil element is subjected to additional load, ultimately causing the soil to fail. The axial strain generated in the sample because of the deviator stress is measured using a dial gauge attached to the loading ram. We collect data on the increase.
Can you remember our soil strain types? One is the volumetric strain, the other one is the shear strain. Volumetric strain is overall soil samples volume changes. In this case, we can measure the water drain out from soils, right? So mostly we can guess the entire soil sample volume change. But in this case, this delta L, which is the shear strain. So if let's say this strain rate is reaches 20%, the traction machine automatically terminated.
Increasing deviator stress and its corresponding strain generated in the sample during the shearing phase. Hence, we can plot a graph between these stress and strain values. If the soil sample represents over-consolidated soil, the graph looks something like this. And for normally consolidated soils, the graph looks a bit different. We already know that over-consolidated soils are those that have experienced higher loads in the past than they are experiencing now. While normally consolidated soils are those that are experiencing their highest load currently. For over-consolidated soils, we observe a clear peak in the graph, followed by a drop in stress and eventually stabilization. The soil sample fails at this peak stress, which is also called the failure stress. Beyond this point, the soil cannot take further load, but the strain keeps increasing. For normally consolidated soils, we do not observe such peak. Instead, the value of stress where the graph stabilizes is taken as the failure stress. In triaxial test, as we mentioned, the sample is stressed in two phases. First, we apply cell pressure, and second, we apply deviator stress. In the first phase, we can either keep the drainage line open, allowing the sample to consolidate, or close the line, keeping the sample unconsolidated. In the second phase, we have similar options. We can either allow the water to drain out, which is called the drained condition, or prevent the water from escaping, which is the undrained condition. So, based on these drainage conditions, there are four possible scenarios for the test: unconsolidated undrained test, unconsolidated drained test, consolidated undrained test, and consolidated drained test. However, the unconsolidated drained condition doesn't make sense. It implies that we won't allow the sample to consolidate in the first phase by keeping the water inside the cell, but will allow water to drain out in the second phase. The moment we allow the water to drain out, the sample will begin to consolidate. Therefore, we can realistically test the soil in these three conditions only. In short, these conditions are called UU, CU, and CD. These drainage conditions are representative of certain real field situations. At least 3 soil samples are tested in order to analyze the state of stress at the time of failure. At the time of failure, we see that the confining stress and the axial stress, which is the confining stress plus the deviator stress, act normally to the surface of the sample. For clarity, we show them like this. We can see these are the maximum normal stresses acting on the soil sample, as no other force is acting on the soil at any other angle. Therefore, they become the minor and major principal stresses respectively. What are these major and minor principal stresses? To understand this better, please watch the shear strength video. We have discussed these in detail there. In short, when a body is stressed, there exist three mutually perpendicular planes on which shear stress is zero. These planes are called principal planes, and stresses acting on them are called principal stresses. Coming back to the sample's state of stress. The axial stress, being the maximum and major principal stress, is denoted as sigma 1, and the confining stress is denoted as sigma 3. Using the data of these principal stresses at failure obtained from all three samples, we plot more circles for each sample. These circles show the stress conditions at failure for each sample. We then draw a common tangent to all three circles, which touches all three circles. This line is called failure envelope. This line is described by this. This also we have learned in our previous video. The slope of this failure envelope gives us the angle of internal friction or angle of shearing resistance. Also, the intercept this line makes at the stress axis is the cohesion. It is important to note that sigma 1 and sigma 3 are the total stresses. In unconsolidated, undrained, and consolidated, undrained tests, we don't allow the water to escape, and we measure the pore water pressure. For these tests, we can also plot the more circles with effective stresses.
The dashed circles means that total stress circle minus just water pressures develops from loading stages. So all more circles shift to left. You see, these more circles, total stress more circles, shifted to left. These more circles, total stress. This more circle, effective more circles. This is the another total stress, and this is the effective. And each more circles has a different confining pressures. Increased confining pressures.
We know effective stress is simply the total stress minus the pore water pressure. When we draw these curves for different drainage conditions, we get different sizes of more circles and different positions of the failure envelope. We then extract the shear parameters from these graphs to complete our analysis. For example, in unconsolidated, undrained condition, where water drainage is not allowed during both the stages of pressure application, if the soil sample is fully saturated, we get these type of more circles. All these circles have the same diameter. So in this case, the failure envelope, the line tangent to all the circles.
In our lab, we are supposed to draw this circle. But let's think through why the circle diameter always same with the different confining pressures. Why do we need to draw this kind of straight line in the UU tests?
It will be a horizontal line. The triaxial test significantly improves our ability to determine the shear strength of the soil compared to the direct shear test we discussed in our previous video. The advantages of the triaxial shear test are as follows. This test accurately represents the real-life stress conditions that soil experiences in the field. Then we have complete control over the drainage conditions during the test. Additionally, it allows us to easily measure the change in pore water pressure and volumetric changes, providing a thorough understanding of the soil's behavior. Then, in triaxial test, sample can fail along its weakest plane, ensuring a natural failure mode. Then, because we track the stress state at every stage leading up to the failure, we can plot a Mohr circle for any shear stage. Next, in the test, the stress distribution across the failure plane is evenly distributed. However, even after so many advantages of triaxial shear test, it has some limitations too. First is that the apparatus is quite bulky and expensive. Then, for drain tests, the experiment takes a long time to complete compared to direct shear test. It is also challenging to accurately determine the cross-sectional area of the specimen at large strains. Also, we assume that the sample remains cylindrical at large strains, which may not always be the case. One more problem is that the test only simulates axis symmetrical problems, whereas real-world issues are often three-dimensional. Well, despite these drawbacks, the triaxial test is extremely useful. It is reliable and accurate in determining the shear characteristics of all types of soils under various drainage conditions. I would like to thank my patrons for support.
So how do you feel about shear strengths of soils? So hope that this video concrete your understanding of the soil's shear strengths. So probably it is quite easy for you to understand what is the CU test right now. C means consolidated U on drains. Consolidated meaning during the confining pressure stages, we open the valve, right? And then our water pressure, 0. In the shearing stages, in the loading stage, the drain valve were closed. It means that no volume change because no water out of our soils, and then but we can measure pore water pressure here, positive delta U. So in the effective stress, the initial confining pressure plus additional deviator stress plus minus water pressures. That's all. According to our drain conditions, we need to figure out development of the water pressures, and then we consider effective stress. In the consolidation stages, the draining valve is still open. So we can measure the volumetric strain. All around pressures applied, and then we can get volumetric strain, not the shear strain. So this soil's volume keep compressed. In the shearing stages, our drainage valve is closed. How come can we measure the soil volume change? Cannot? Cannot. So in this case, we only the way we measure the soil's volume change is image record. This is our initial soil sample. Before apply load, we take up pictures and then send it to our AI models to capture the volume of soils. And then after compressing our soils, these soils looks like bulged, right? Then take a photo but it is kind of different shapes, but hope that water cannot be drained out. The total volume would be the same, but we have different soil sample shape. So similar to the CD test, we have a dense sand or OC clay, we have a peak value. And then loose sand and normally consolidated clay, we have a non-peak and then reached the critical state. Can you see that after peak value, the actual strain increase without increases in deviator stress. In these stages, we called critical states of the soil and consider as failures. When it comes to your volume changes, so normal consolidated keep on changing, and then the dense sand or C sands looks like this kind of shapes. And then we have these stress strain behaviors, and then such stress conditions can be represented by more circles. Here is the confining pressure and plus the deviator stress. Confining pressure plus deviator stress. And then we draw the straight line for the failure. In this case, U meaning on drain. Wow. Hi, Prof. On drain means we can measure water pressures. So we can draw another two more circles, which is the effective more circles. This lead, small less circle, total stress more circle, and then minus out for water pressures. The large less circles minus out for water pressure becomes large green circles. So this red line is the total stress failure envelope. The green line is the effective stress failure envelope. This can be happens because we close the valve. So we can get certain our shear strength parameters in terms of total stress, in terms of the effective stress. Once you obtain this, we need to determine which parameters can be used in our design. It depends on you, depends on your engineering judgment. Effective total failure envelope, effective failure envelopes. This parameter can be applied to embankments, but rapidly over the soft clay deposits. Somewhat rapid, also rapid in the slope stability because it is on drain conditions. Drain and on drains is kind of a different rate of loading versus rate of excess water pressures. Drain means the loading rate is quite low. On drain, loading rate quite high. So no time to dissipate of the excess water pressures. Now we can consider unconsolidated on drain. Wow. Close the valve all the time. In your laboratory is the UU. So you never open your port pressure valve. It means that your clay soil sample is now fully saturated, and then the water inside the clay never drain out. But we can't measure volume changes, but we are able to measure pore water pressures. In the initial conditions and then the shearing conditions, we close all the valve. So initial volume of sample is area times height. And during the shearing, the soil volume also area times height. They are all same. What is important step in the test on the on-drain condition is the correct your soil sample area when data processing. This area is the initial area, right? For example, this is the your soil samples, but you can compress. Oh, can you see? Compress. You see this cross-section area same as this? I don't think so. So we need some area corrections. Fortunately, Prof. Ho Jiahui explains such corrections, data processing of the triaxial tests under UU. So I've recorded the Prof. Jiahui's lectures, and then I will share these recordings to our exercise. So it is hope that you are able to understand how to process the laboratory results. please make sure that if you have some questions and need something to be clarified, you might approach to me and Dr. Joel. Okay, do not disturb Prof. Hojiawi. Okay? In the UU tests, U means unconsolidated. Close the valve. Another U is undrained. We still the valve is closed. It means that in these two stages, we can measure pore water pressures. We apply confining pressures. It means that these confining pressures developed water pressures. These increments of your water pressures and your increments of the confining pressures. This ratio represented by B, letter capital B, so-called B value. Professor Scampton developed this concept. The Scampton water pressure parameters, Scampton parameters, just simply B value. This increments over increment of your confining pressure values larger than 0.95. Oh, this soil now fully saturated. Theoretically, we should have 1. But in realistically, I never seen unity before. The maximum is 0.98. This is the unconsolidated consolidation stages. What about undrained during the shearing? We apply deviatoric stress. And also we expect that there should be water pressures. Increments of water pressure due to this deviatoric stress. And then your deviatoric stress increments. These two variables ratio represented by A, capital A, Scampton water pressure parameters. Hi, Prof. I understand that B values can be used in the checking of the saturation conditions. Yes, but A, how can we implicate what situations we are going to use A? Okay, later on. So in the stages 2, we will get B parameters. In the stages 3, we will get A parameters. So our total water pressure increments at any stages, delta U can be expressed in terms of B value, A value. In terms of the B value, always corresponded to degree of saturations. Theoretically, once you have 1, your degree of saturation is 100%. What about 0.9 something? Still almost 100%. And then the typical parameter A. A tells you about the sensitivity. NC clay looks like low sensitivity. Apply load, your strain increase smoothly. And your portable development looks like that. So in this case, your Scampton port pressure parameter A ranges from 0.5 to 1. But in this case, for highly sensitive clay, your strain stress curve looks like that. And then your A parameter is greater than 1. So collapse of soil structure may occur in a high sensitive clay due to very high water pressure generations. You can imagine that your play dough, even your baking the dough, you put more water, it looks very sticky and very deformable, right? This is very highly sensitive status. And then well-maintained play dough and clay and very soft. I mean, in terms of the very playable, easy to play with the dough. It is the low sensitivity. In terms of OC, it is still likely over consolidations. Looks like that. Your A parameters range up to 0.5. And even you have negative. Why? Your port pressures negative. Why? This is over consolidated and keep pressing. So your soil particles slide over the particles. The volume increase and you see more space, which is the negative suction pressure occurred. So your measured port pressures looks negative. That's why your A parameter is negative 0.5 to 0. So this is the empirical chart, empirical graph for in terms of the relationship between A at failure to over consolidate ratio. In the UU test, we're supposed to have circle 1 for your group, circle 2 your friend group, circle 3 your another friend groups. You can collect all together, combine together, and 3 groups draw these such more circle combinations. 3 group has 1 undrained shear strings. For example, your group confining pressure 50 kilopascal, and then failure at 150. Your friend group confining pressure 100, failure at 200. Your friend, another friend, confining pressures 150, failed at 250. Or your circle, the diameter should be same. Why? For examples, your friends group starting at 100. So off the top of my head, high confining pressure means these soils withstand high deviator stress. So my expectation is larger, more circle, but still same diameters with yours. Why? These circles is total stress and minus out your port pressures, which is the effective stress more circle. When we adopt to have a effective stress analysis on unconsolidated undrained traction tests, then as the test is undrained, therefore excess deviator stress is taken up by water, which increase the port pressure, right? Deviator stress applied and your port pressure resists this deviator stress. It means that whatever increases in deviator stress, maybe it goes in increasing your port pressures. So increases in effective stress equals to 0. That's why every single circle with different confining pressure has same diameters. So initial effective stress remain unchanged, and the changes in your port pressures does not affect the total stress applied. So your more circles were obtained, and so you have a unique more circle in terms of effective stress. This is not the triaxial tests, just unconfined compression tests. Simply prepare your soil sample, just put on certain loading lamp and directly apply deviator stress. It looks similar to UU test results, but confining pressure, 0. Just atmospheric confining pressures. So these unconfined compression tests quite quickly done and easy to obtain properties and easy to guess the consistency. Oh, this is quite soft and very hard.